In December 1998, a Delta I rocket lifted off from Cape Canaveral carrying the Mars Climate Orbiter. Between spacecraft development, launch logistics, and mission operations, NASA had invested nearly $328 million into this single scientific mission. Fast forward to September 23, 1999. Inside the Jet Propulsion Laboratory, mission controllers are waiting. The spacecraft has just executed its Mars orbit insertion maneuver, firing its engines to slip behind the planet. And the team is listening for the signal to re-emerge. The expected time of reacquisition passes, the silence continues, the signal never returns, and the world realizes the multi-million-dollar spacecraft has disappeared. But the initial investigation found something completely unexpected. According to the final telemetry data, every physical instrument, thruster, and solar panel had functioned perfectly right up to the moment of the blackout. Since the hardware was in perfect working order, investigators were forced to look at another variable, the invisible exchange of information between the human operators and the machine's code. To understand what happened, you have to look at the spacecraft's design. The probe had an asymmetric solar array sticking out of one side. In the vacuum of space, that array caught solar wind like a sail, applying constant pressure that caused the spacecraft to slowly spin off axis. Internal reaction wheels absorbed that spinning momentum. When those wheels maxed out, the spacecraft fired small thrusters to bleed off the excess energy. This was a routine maintenance task called an angular momentum desaturation, or AMD burn. Two different organizations manage the software for these burns. Lockheed Martin built the ground software that tracked the physical force of the thrusters, while NASA's Jet Propulsion Laboratory, JPL, built the navigation software that received that data to plot the spacecraft's course. Lockheed Martin calculated thruster force in Imperial units measuring impulse in pound force seconds. JPL software assumed incoming data was metric, reading the numbers as Newton seconds without conversion, because 1 pound force equals 4.45 newtons. Every thruster calculation was understated by a factor of 4.45. This unit mismatch meant that routine mechanical maintenance was actually injecting a silent compounding error into the spacecraft's trajectory that the computers could not see. Because of the asymmetric solar arrays, these AMD thruster burns happen 10 to 14 times more frequently than the navigators originally expected over the 286-day cruise to Mars. With every burn, the two realities split. The computer modeled a safe path, while the physical spacecraft was shoved incrementally off course. Navigators spotted anomalies in the trajectory tracking data weeks before arrival. However, because the software reported no syntax errors, the anomalies were dismissed as normal data noise. This investigation breakdown notes the navigation team was oversubscribed and lacked peer review. A contingency maneuver to raise the orbit was discussed verbally, but abandoned without formal plans. This rigid culture forced the team to trust a flawed data pipeline over physical trajectory anomalies. On September 23, 1999, the probe prepared for Mars orbit insertion. The navigation computers believed the probe was skimming safely above the Martian atmosphere at an altitude of more than 140 kilometers. The physical truth was different. The mathematical error had actually driven the probe down to an altitude of just 57 kilometers. At that low altitude, the atmosphere is far too dense. Extreme friction and heating violently ripped the functioning spacecraft apart. This summary from the Mishap Investigation Board shows the failed conversion of units as the immediate trigger, but they categorized it under a much larger list of process and social problems. The mission failed because there was no end-to-end integration testing between the two organizations. The Mars Climate Orbiter remains a warning of how a single unchecked assumption can compromise a multi-million-dollar mission, making rigorous end-to-end testing a requirement for mission success. End of report.